a little tutorial on, it's called the electromagnetic spectrum of light. Let's set the context for this a little bit. In astronomy, most everything that we know about any source is coming from light that is in some part of this electromagnetic spectrum, from radio to gamma rays. There are a few cases where we get cosmic rays, so individual charged particles from sources in space, and there are a few cases where we detect sources through their gravitational radiation. You can literally count those sources just sort of on your, well, it's getting up to close to 100 gravitational wave sources, so not necessarily on your hands and toes in a convenient way, but you're talking about something like 100 sources. Everything else is coming from light. So to understand astronomy, then, we need to have at least some understanding of this rainbow, this spectrum of electromagnetic waves. So we have it organized by names: radio into microwave, infrared, visible, ultraviolet, X-rays, gamma rays, and there's not, you'll see there's like some overlap, like whether a part of the spectrum you would call it X-ray or gamma ray sort of depends upon where your field is and what their convention is. There aren't hard and accepted rules for X-ray light ends at this frequency and gamma rays start at this frequency. There's overlap, and that's fine. It's not the biggest deal in the world. The next part of this figure, we have the electromagnetic spectrum organized by frequency. So frequencies as low as like 1,000 cycles per second up to 10 to the 23 cycles per second. So we're going through 20 orders of magnitude. And then the wavelength in meters, going from, is labeled 10 to the 4th, so 10 kilometer wavelength radio waves, to gamma rays at 10 to the minus 14 meters. So smaller than an atom, 10 of them could fit across a nucleus. And there's no actual limit on one end or the other. Radio goes on forever to longer and longer wavelength, and gamma rays go on forever to shorter and shorter wavelength. As far as we're concerned in this class, there's no end to the electromagnetic spectrum on either end. So radio doesn't end, and gamma rays don't end. All right. So let's go through these questions. The electromagnetic spectrum of light is often arranged in terms of frequency. Which one of the following has the highest frequency? Well, the high frequency end is gamma rays. The electromagnetic spectrum of light can also be arranged in terms of wavelengths. Which one of the following has the longest wavelength? So the long wavelength end is in the radio. So radio waves. Which of the following types of light travels at the fastest speed? As always, is tripping people up. It is all the same speed. Speed of light is the speed of light. In this relationship between frequency and wavelength, the frequency of an electromagnetic wave times its wavelength is traveling in vacuum is equal to the speed of light in vacuum. And so this is how the ordering is working out. High frequency must be a short wavelength because their product has to equal c. And a low frequency has got to be a long wavelength because, again, their product has to give you that same value of c, the speed of light. So ultraviolet light, microwaves, X-rays, radio waves, gamma rays, infrared light, visible light, all parts of the electromagnetic spectrum are following the same equation. They're all traveling at the same speed, speed of light, c. All right, let's try some more questions. So So another property of light is the energy. Which of the following has the greatest energy? Comic book fans will know. The high energy end of the spectrum is also the high frequency energy, or the high frequency end of the spectrum, and that is gamma rays. The energy stored in a photon is Planck's constant h times the frequency. So the higher the frequency, the higher the energy. All right, we have our discussion between our two friends, student 1 and student 2. Consider the following discussion between two students about the different properties of light. Student 1, I think I get how light works. If you look at the chart of the electromagnetic spectrum, it shows that light with a higher frequency will also have a long wavelength, but it all has the same speed. Student 2, I disagree. If one type of light has a lot of energy and a high frequency, it will have a faster speed than light with a lower energy and a lower frequency. So do we agree or disagree with either or both of the students? Explain your reasoning. So they are actually both wrong this time. Student 1 is wrong in that it shows that light with a higher frequency will also have a long wavelength, and that cannot be true. If it has a high frequency, it must have a short wavelength, because wavelength times frequency is equal to a constant. Student 2, what they got wrong, if one type of light has a lot of energy and a high frequency, it will have a faster speed than light with a lower energy and a low frequency. So student 2 is correct about energy being proportional to frequency. That's good. But they all travel at the same speed of light. So they're both wrong in their own unique and special way. All right, question 6. Complete the following sentence describing the relationship between the energy, frequency, and wavelength of light using the words highest, lowest, longest, and or shortest. The portion of the electromagnetic spectrum of light with the greatest energy has the highest frequency and the shortest wavelength. So greatest energy is highest frequency and shortest wavelength. Let's see, the visible light portion of the electromagnetic spectrum of light is often subdivided into the colors of red, orange, yellow, green, blue, indigo, and violet. So this is your Roy G. Biv. Using the words greatest, least, highest, lowest, fastest, slowest, longest, and shortest, write a sentence or two that describes how light at the red end of the visible portion of the spectrum and light at the violet end of the visible light portion of the spectrum compare in terms of their energy, frequency, speed, and wavelength. All right, so let's see if we can do this. Red light has lowest frequency, longest wavelength, lowest energy, and same speed out of the visible light. And then at the violet end, so violet light has highest frequency, shortest wavelength, highest energy, and same speed as the rest of the visible portion of the electromagnetic spectrum. Okay, and a few more questions. For each of the statements A through D provided below. Circle the word choice that correctly describes how the two forms of light compare. Infrared light has greater or less energy than ultraviolet light. It has to be less. So lower frequency and a longer wavelength. X-ray photons have longer or shorter wavelengths than gamma ray photons. So gamma rays are more energetic than X-rays, and so the X-ray photons have a longer wavelength than gamma ray photons. Visible electromagnetic radiation has a higher, lower frequency than radio wave electromagnetic radiation. So visible is higher frequency. And infrared light has a faster, slower, same speed than microwave light. They all travel at the same speed. Alright, last question. Of all the types of light the sun gives off, it emits the greatest amount of light at visible light wavelengths. It actually peaks right around the color of green. If the sun were to cool off dramatically and as a result start giving off mainly light at wavelengths longer than visible light, how would the frequency, energy, and speed of the light given off by the sun also be different? Explain your reasoning. So we're going to go from peaking in the visible to longer wavelengths than visible. So that's in the infrared. So that means frequency decreases, energy decreases, and the speed does not change. All right, and our relationships for figuring all of that out, we know that wavelength times frequency is equal to the speed of light, so lambda times f equals c. Energy is Planck's constant h times the frequency, and if we instead know the wavelength, that's hc over lambda. So as lambda is increasing, frequency is going to have to decrease because the speed of light remains the same, and as the wavelength increases, the energy is decreasing.